Okay, so suppose you fired a rifle bullet straight up from the surface of the moon. What speed would it need to escape the moon's gravity? Okay, so we're not really going to use that. We're not going to really use that. That's kind of stupid, right? What speed would it need to escape, right? So we're going to have to shoot it. This does not escape. This goes up 534 kilometers and falls back on the moon. But there's some velocity that will escape, right? So what I'm going to do is I'm going to set this thing up. Here we are, right? On the moon. There we are, firing the rifle up. And infinity is out here. Again, there's a little sign there. And basically the lowest speed you can give it, the escape velocity that it will get to infinity, is such that when it reaches infinity, it stops, right? Now, if you think about this, at infinity, it's not moving, so it doesn't have any kinetic energy. It's at an infinite radius, and so it doesn't have any potential energy. The total energy at infinity is 0. That's fun. And when you're sitting here on the surface, you're giving it a positive kinetic energy, but it has a negative gravitational potential. And the only way that it can be 0 afterwards is that it was 0 to begin with, right? So if you fire a rifle bullet with the minimum velocity it needs to escape the moon's gravity, when you fire it, the moment you fire it, it has 0 total energy. That is, it's got potential energy equal to its negative gravitational potential. That's fun, isn't it? Has 0 total energy. Objects that are gravitationally bound to mass objects like this have a negative total energy. That is, they're somehow trapped in that well, right? Remember the gravity well, the sheet of rubber, right? They're somehow trapped in there, and so this should go to 0, right? That should be 0. Okay, they're trapped. They're somewhere down in this well. Objects that are up here that are moving and have escaped and are still moving have positive total energy. That is, they have more kinetic than their negative potential energy. Okay, so this is a fundamental problem here, right? All right, so let's solve this problem. What we're going to say is that the object, when you fire it, has kinetic energy, and then it's got negative gravitational potential energy, right? And then when it reaches infinity, it has 0 energy, right? It's not moving, doesn't have any potential energy, right? Notice that the little mass cancels like this. And if we just do math here without doing any numbers plugged in, let's just do that, right? We get 1/2 v squared is equal to g big M over r. So I just put that on the other side, right? And then I get v squared is 2 gm over r, and then I square root that. And I get this equation, which is in the data packet, right? Okay, that's the escape velocity, and that's where it comes from. The 2 comes from the 1/2 of 1/2 mv squared. So our escape velocity, which is what we're asking, is the square root of 2 times 6.67 e minus 11 times 7.35 e 22. Notice that it was the bullet's mass. The bullet is moving. The bullet's mass cancels. The moon's mass does not. Divided by r. And r is how far you start from that mass, right? The closer you get, the faster you got to go to escape from that mass. And this is true of any mass, right? Not just black holes and moons and things like that. E22. Whoops, what am I doing? 1.74 E6. I knew it was one of these numbers here. Okay, so square root. Oh, my calculator turned off. Square root. My calculator got bored with me. How sad is that? Okay, so I'm going to go 2 times 6.67 e minus 11 times 7.35 e22 divided by 1.74 e6. I'm getting 2373. And the answer at the bottom is slightly off because I used a different value for that. That is the escape velocity. Okay. Now, just for fun, we're not really going to talk about astrophysics in this class, but there really is no problem with this thing being faster than the speed of light. The speed of light is 3.00 times 10 to the 8th meters per second. Well, no mass object can go, or any object can, even information can't go faster than the speed of light. And so if the escape velocity from an object becomes faster than the speed of light, that's what a black hole is, which is kind of fun. Now, everybody thinks that, and this is conventionally true, right, that black holes become black holes, that this number approaches the speed of light, which is a very large number, by this mass getting super big. And to be sure this is true, there's masses with millions and millions of solar masses, right? Probably billions out there, right? And that's, of course, a very massive thing. Will have an escape velocity from it that's faster than the speed of light. But there's another intriguing way, and that is if the radius just gets small enough, right? If you take the Earth and somehow could pack it into something the size of a marble, the Earth would be a black hole. It's just that there's no known way to do that. But there were people when they fired up the Large Hadron Collider that speculated that they would create a miniature black hole that would swallow everything. And anyway, yeah, I'm going off on a tangent, so sorry about that.